Hi guys, today I will start a new series of lectures. The topic is real analysis. Okay, so first of all, what is a real number, right? We can begin with natural numbers in here, right? Then natural numbers start from 1, 2, 3, 4, and all the way goes to infinity, right? This is natural number, right? And then we can look at the irrational numbers. Irrational numbers are, let's say, 0.5, 1.5, right? And even though we see the combination of natural numbers and rational numbers, there are still some gaps in between them, right? So a real number, it is continuous all the way from infinity, negative infinity to infinity. There are no gaps in between, right? For example, if we zoom in this 3, 4 range in here, right? Real numbers including this point, which is 3.00001 or 3.00001, and all the way goes to 4. So there are no gaps in between 3 to 4. So this is the main concept of real numbers. And so the first chapter we're going to look at it is called the completeness of real numbers. Okay? So the first concept we're going to learn it is called suprema and infima. So let's imagine A is a subset of real numbers, and a real number m, capital M, is the upper bound of A if for all of x in A, x is less than that m. And same thing for lower bound, right? If little m of R is a lower bound of A if x is greater than equals to little m for all x in A. Right? For example, our set in here is 0 to 1, right? And again, 0, 1 number, the boundary of the 0, 1 is not in this set, okay? We consider this m is the upper bound of A because for all x belongs to 0 to 1, it is all less than this capital M, right? Same thing for this little m in here, right? So for all x in between 0 and 1, it is all greater than or equals to this little m. So therefore, capital M and little m are upper bound and lower bound of this set. Okay, so let's look at the example in here. So consider a natural number set, right? From 1, 2, 3, all the way goes to infinity. And it is bounded below, yes, right? We can consider 0, right? This is not a 0. So consider a number 0, right? So 0, it is less than all the numbers in the number set. So of course, so 0 is a lower bound of natural number, right? So therefore, natural number, it is bounded below. And it is bounded above? No, right? Because natural numbers can be all the way goes to infinity, so it's not bounded above. Okay, so let's look at another definitions. So let's suppose A is a subset of real numbers, right? And again, if capital M is the upper bound of A, and this capital M is less than is less than every upper bound of A, then it is called a supreme of A. Okay, I denote as here. For example, in here, right? Again, the same sign in here, right? 0 or 1 in here. Okay, so consider this is capital M prime, prime, right? And this is what do you have in here? It is the upper bound of A. It is actually the supreme of A because this m is less than or equals to any other m. So therefore, this m is the supreme of A. Okay, so same thing for infima. Infima we denote in here, right? This is an infima of this set because this little m is greater than or equals to any other lower bound of A. Okay, so this is concept of infima and suprema. A super important note in here, it is suprema and infima may or may not be the set. For example, right, if if we have a closed boundary of it, oops. Right? So if we have a closed boundary, if we have an open boundary of 0 to 1, right? So suprema, if it, so the suprema will be 1, right? And infima would be 0, right? Again, 1 and 0 is not in this set. But if we look at a closed interval, 0, 1, right? Again, same thing, suprema is 1, right? And infima is also 0, right? But 0 and 1, it is in this closed set. So therefore, suprema and infima may or may not be in this set. Okay, so let's look at this example in here. So let's suppose A is a subset of your real number, and A is equals to x1, x2, or xn, right? And also it is bounded. How do you know it's bounded? Because we have a finite number in this set A. Okay, so what is suprema of A? So the suprema of A will be the maximum of x1, x2, xn, right? It is easy to understand. And also the infima of A will be minimum of this set. Right? This is simple, right? And also let's look at another example. Also this A, the subset is also this A, it is a set of 1 over n where n belongs to a natural number. So what is actually set? So this set will be 1 over 1, 1 over 2, 1 over 3, and also it goes to 1 over like a large number, right? And also it goes to infinity. Okay, so what is the suprema of A? So the suprema of A will be is minimum of the is a minimum upper bound of it, right? So and then what is upper bound of it? It's just simple 1, right? So suprema of the suprema of A is just 1 in here. And infima of A, what is infima of A, right? So the smallest number will goes to super close to 0, right? But it will never reach to 0. So therefore, the infima of A will be 0, right? And we know that 1, it is within this A, but 0 is not in this A. So yeah, so again, this topic, right? And also another example, right? Again, we have saw this example earlier. So we can draw it in here. This is 0 and this is 1, right? A suprema of A is obviously 1, 1. And infima of A is 0. And again, 0, 1 is not in this set. But if you look at A is equals to a closed interval of it, right? Closed interval means 0 and 1, it is in the set. The boundary of this interval is in this set. And 0, 1, again, suprema is 1 and infima is 0. And 0, 1 is in this set. Okay, so let's look at another example. So let's look at another theorem. So every non-empty set of real numbers that is bounded above has a suprema. Okay, so we can actually draw in here, right? Again, we have a non-empty set, right? So again, a non-empty set, and also it is bounded above, right? So bounded above, let's just draw in here. Okay, so this is a boundary above, right? So we can consider this is its boundary, and also, so very obviously it has a suprema in here, right? And we can consider that the lower bound of it. So we know that infima of A it is equal to the negative of suprema of its negative A, right? So therefore we can get another theorem which is every non-empty set of A which is bounded below has an infima. Okay, so let's look at this example in here. So we have a set of A which is element is x, it belongs to a real number such that x is less than square root of 2. Okay, so what is the suprema of it? We can draw a line here, and this is square root of 2, right? And okay, so again, so suprema is just square root of 2, right? But let's consider another example where x is actually belongs to a rational number, okay? A rational number. Then what is the suprema of a? We can know that, so rational numbers, again, square root of 2 is not a rational number. It is a irrational number. So square root of 2 is it is not part of this set B, right? So therefore suprema of a, it just does not exist. Does not exist. Let's look at another topic, Cauchy sequence. So definition of Cauchy sequence is, imagine a sequence xn of real numbers is Cauchy sequence if for every epsilon is greater than 0, there is a capital N such that the distance between 2 points is less than epsilon for all n which is larger than a capital N. I know it is like what the heck, right? So let's actually look at an example. So let the xn be be the set of 1 over 1, 1 over 2, 1 over 3, 1 over 4, like 1 over 100, 1 over 101, 1 over 102, and now we keep going, right? So let's set the epsilon is equals to 1 over 100. Okay, and the capital N, it is 1 over 101, right? So if we draw the line here, and this is 1, this is 101, 1 over 100, and this is 1 over 101, 1 over 102, right? And here, right, we set our N equals to not 101. So that's that N equals to 102, right? So x of capital N is equals to 1 over 102, right? So let's set m is equals to 103 and little n is equal to 104, right? 103, 104. So therefore x of m is equal to 1 over 1 over 3, and x of n is equal to 104, right? And here 103, 104. Okay, 104. So therefore the distance between these 2 points is actually less than our epsilon, which is 100, right? And we can set mn is any number which is larger than 102, and the distance between x of n and x of m is always less than that epsilon. So therefore this sequence is Cauchy, right? And let's actually look at this theorem here. So a sequence of real number converge if and only if it is a Cauchy sequence. Okay, so we have to be careful of this if and only if statement. It is a combination of a forward implication and backward implication. So the forward implication is a sequence of real number converge, then it is a Cauchy sequence. And the backward means if a sequence is a Cauchy sequence, then that sequence converge, right? So let's look at the first. So let's look at the above examples again. Right, we know that this sequence it converge to 0, right, but never reach to 0. Okay, so 1 here and 0, and this is 1 over 2, 1 over 3, 1 over 4, little number in here, 1 over 100, this is 1 over 101, right? And this sequence actually converge to 0, right? And we prove that it is a Cauchy sequence. And since it's a Cauchy sequence, and this number can be super small, almost reaches 0, but never reaches to 0. And so therefore it is a So this sequence is also a converged sequence. Right, so we have finished the topic for today. So the first part of lectures we covered the suprema and infima of it. And the second lecture we covered the Cauchy sequence. Okay, so from today's lessons we have a super broad idea of what is the real numbers and like how does real number works. Thank you.